All right, BC kids, here we go with the last section in Unit 9. It's called the area bounded by two polar curves. It's going to take what we learned in the last section, 9.8, and add just a little bit more to it. So recall the area bounded by a polar curve, this was what we learned in the last section, is 1/2 the integral from alpha to beta, my angles, of r squared d theta. And r was your f of theta, whatever they give you there. So things to watch for when using more than one polar curve for area are points of intersection. They're going to be huge to us. And symmetry. Use symmetry whenever you can, because that's going to help you out with it not being such a large equation. You can kind of do things a little more simply. All right, so here's what it says. Find the area of the region common to the polar curve of r equals 4 cosine of theta and r equals 2 sine of theta. And you're like, what the heck? I have no idea what that looks like. So you're going to go to your handy dandy calculator and you're going to graph on your handy dandy calculator these. Now hopefully by now you know if it's a cosine, it's going to lay on the x-axis, and if it's a sine, it's going to lay more on the y-axis. So here's what happens with this guy. I'm not the best of drawers, but here you go. My 4 cosine of theta is going to be like this, circle. And then my 2 sine of theta is going to be smaller, and it's going to be up on the y-axis, like this. And so the area that I'm actually looking for, and I would grab a highlighter because we're going to be doing this for every problem, looks like this. It's that area between the two curves, the area bounded by the two polar curves, which is what they're looking for. And so the big question is, where do they intersect? Well, how do you find where any two equations intersect? You set them equal to one another. So that's what we're going to do. You have 4 cosine of theta equals 2 sine of theta. All right, well, let's think about this. If I divide 4 divided by 2, I get 2. And if I divide by cosine, I end up with sine over cosine, or 2 equals the tangent of theta. Sine over cosine, remember the old quotient rules from pre-calc? And I don't know what that is. That's not on the unit circle where it would actually equal a 2. So now I've got to go to my calculator and think about where the inverse tangent of 2 would be located. What would be the reference angle for that? And I get 1.107. That's your theta value. So you know down here it's at 0, that your theta is at 0. And you know up here at this point of intersection that your theta equals 1.107. But there's an issue with these, and here's what's kind of weird and interesting, I guess, at the same time. If I were to look at this thing, remember how you can take like right minus left? Back in the days of when we were trying to revolve things and find areas between curves, that you would take right minus left or top minus bottom, whatever that might be. This one, it changes right here. If I were to draw a line and intersecting those two intersection points, you see how I have some area that's below and some area that's above. If I could zoom in, I would, but I can't because of the camera I'm using. So what I really need to do is find the two areas, because what's on the right changes. This one is a right minus a left kind of thing, because I've got a bounds here this way that are these theta values. So I'm going to put two areas together. I'm going to put one area formula for this side of the line and one area formula for this side of the line, to the left of the line. All right, so here it goes. I have the area, doesn't change. It's 1/2 the integral My right function is the sine function because it's the little circle along the y-axis. So I have 2 sine of theta squared d theta. We'll talk bounds in a second. And then I'm going to add that with the one that's over here. Now this one that's over here is 1/2 the integral. And it is, if I look at the functions here, it's the 4 cosine of theta squared d theta. But then the question is, what are the bounds? Well, the first set of bounds go from 0 to the point of intersection. 0 to the point of intersection. So this one is 0 to 1.107. And the second one has to pick up from that same point, 1.107. But where do I get to connect this back to 0 again? Hopefully you're thinking of, oh wow, that's at pi over 2. And so that's your story. That's what you got going on here. So you have to graph it first. You've got to figure out if when you intersect the 2 intersection points, do you have different bounds? Like, do you have different values? Like this one has the sine function, this one has the cosine function. So you need to take them into account. And so you put that in your calculator, you add them up, and you get an area of 0.962. And so there's example number 1. Example number 2 is a whole different area, a whole different scene. Now this time they gave you a picture. Find the area of the common region to the polar graphs of r equals 2, that's the circle, and r equals 2 minus 2 sine of theta, and that's this guy here. So where are they common? And you're looking at this area in here. Again, this is a good section for a highlighter, so you can visualize what section you're talking about. So now thinking of your points of intersection are going to be here and here. But you might think, because of symmetry, do I really need to figure out this whole thing, or can I just figure out what it would be for half of it and then multiply it by 2? And the answer is absolutely. Use symmetry as much as you can, because otherwise it's going to get into larger equations that are a little bit harder to integrate. So I know that if I only take this part, that it's half the area that I'm really looking for. And it's good to note that. All right, now I need to figure out what it's going from and to. So think about this for a second. I'm really starting down here, right? That's where that area starts. And I'm stopping here because I'm only looking at half of it. Maybe I should put them in different colors or something. But I'm looking for these 2 points because that's the area that I'm checking out here. So when I look at my integral, it's going to be 1/2 the integral. And down here, if I'm looking at it this way, if I'm looking at this is at 2. This is my r of 2. See how it's part of the circle? My r of 2. So it's a 2 squared d theta. And I'm going to add that with, I'm going to talk bounds in a minute, I'm going to add that with, now, the integral that is the other guy. This, when I'm up here, now I'm closing it off with the other r formula. So it's going to be 1/2, I forgot him. 1/2, and it is 2 minus 2 sine of theta, quantity squared d theta. So I have to think about my bounds. If I'm down here, as I start this, remember I'm just doing this one area over here. This is 3 pi over 2, but what else can I call that? And I'm hoping you're saying negative pi over 2. And when I come to this place here, see how it starts, like this is where I'm going to stop, my next place, because now I'm looking at the other curve when I get to this place. Now they're intersected. So this is 0, which means those are zeros. And to close this out, to get this extra part in here, this location going from this is 0, this guy's pi over 2. It's kind of like you're reading it like the unit circle would be. And so I know that 1/2 my area, I go to my calculator and I put in this whole hot mess. And the whole hot mess gives me 3.8539. By the way, if you're having trouble integrating these, catch me up in class and I'll show you on the calculator. But we've done them enough. I kind of feel like you know how to do that. All right, double it. 7.708. There's your area. That's the area for that part. So I found the area for this part being 3.8539, and I doubled it to get the entire area. Number 3. Find the area of the region common to the two polar curves of -6 cosine of theta. That's your circle that is along the x-axis. And then r equals 2 minus 2 cosine of theta. That is your polar guy with the little pointy center there. So what area am I really talking about? It's bounded by the two things. It's kind of like this egg that's in the middle. Egg in the middle. All right, so find the area of this region. So I'm going to look at this, and again, I want to know the points of intersection, right? I want to know these points of intersection for this guy. So, in looking at this, I'm going to take -6 cosine of theta equals 2 minus 2 cosine of theta. Which, by the way, I know in a lot of these we've been setting up the area formula first. I guess we could do that too for this guy. The area is going to be, can I use symmetry for this? And the answer is yeah. What if I took and just found what it was for this top part? And then I could take, that would be half the area that I'm really looking for. So I guess I could absolutely do that. If you want to start with the area formula, let's go this way. Area is 1/2 the integral. Well, what's your right function? That's the circle. So that's going to be your -6 cosine of theta squared d theta. And then I'm going to add that with, we don't know bounds yet. We're going to talk those. That's what I started to do. But let me put the formula because that's what we've been doing. Keep it consistent. 1/2 the integral, and now I'm looking at the other side of this, which happens to be the 2 minus 2 cosine of theta. So 2 minus 2 cosine of theta quantity squared d theta. But then you get into the bounds, okay? So now you got to figure out the bounds. So that's where I was over here. If I, what do I do? If I add 2 on, now I'm at -4 cosine of theta equals 2. If I divide by -4, I get the cosine of theta equals 2 over -4 or -1/2. And so I want to know where that happens. And luckily it's just a theta and not like a 2 theta or 3 theta or something. So I end up with 2 pi over 3 and 4 pi over 3. Well, let's see what makes sense in my particular function here, in my particular value. So if I look at where this thing starts, and this is totally, you want to trace it on the graph. So I'm going to put that right here. I'm going to put a little note. In fact, I'll put it in orange just to make it stand out a little bit. You want to trace the graph. So you're going to put these in your graphing calculator, and you want to know where these things intersect. What's this value? You want to know what this value is and what, well, I guess that's pretty much it because we're only doing the top part of this, right? So if I were to take those two things and figure out what those values are, it turns out, and this is from tracing it on the graph, that you end up with this being pi over 2. This is a theta of pi over 2. This is a theta of your 2 pi over 3. And then it closes up here. Well, where's that? And if you think about it, it makes sense. Theta is pi. So I'm looking at, here I am looking at the, like if I do those lines, I have from pi over 2 to 2 pi over 3 has my outer part being the circle. That's this guy. So that means his bounds are pi over 2 and 2 pi over 3. And then you pick up again at 2 pi over 3, that's here. And now I'm looking at the other function, this 2 minus 2 cosine. That's this part of the function. And that goes 2 pi. And so you go to your handy-dandy calculator and you get that value. Oh, by the way, this is only half, right? Because I'm using symmetry. So when I get this answer, I want to double it. And so that's going to give me, once you put that all together, an area of 15.708. That takes care of number 3. And again, if you have calculator issues with this, holla in class and I'll help you with those. All right, here comes the next one. Next one is, if I have 2 curves and I want to figure out an area kind of like this guy here. I want to know that area. How do you figure that area out? And so here's what you've got. I'll give you 2 formulas. I'll give you the first formula is 1/2 the integral from alpha to beta. Somebody's driving by saying hi. And I have R2. This is your outer radius, R2. This is your inner radius, R1. So it's going to be R2, your outer radius squared. This just remind you of something else? Minus 1/2 the integral from alpha to beta of your inner radius squared. Hopefully it's reminding you back when you were doing like washer type stuff, right? Doesn't this kind of remind you of the washers? So ultimately it's 1/2 the integral from alpha to beta of R2 minus R1, actually R2 squared minus R1 squared, and then it's d theta. So it's not R1 minus R2 quantity squared, which is what I started to write down. That's really bad because that's what most people get mistaken with this. But it's the outer radius squared minus the inner radius squared. Capital R squared minus little r squared-ish. But now we're talking polars. Okay, so there's a formula that we're going to look at, and we're going to try number 4, our last example. Then there's just a couple of practice problems I'm going to do with you. Okay, so here it is. Oh, they gave us the picture already. Shoo, that's sweet. So what you're doing is find the area of the region bounded by the 2 polar curves r equals 1. There's your circle. R equals 1 minus the cosine of theta as shown in the graph below. Find the area of the region bounded. So what we're going to do is use symmetry again, but I'm only going to look at this top part. I don't know if you can see probably can't see much of my highlight on that. So let me go this way with it. I'm looking for this guy. That's going to be my area, and then I'm going to double it. So just like we did in the others. So I'm going to have, and I also need, right, this is where it starts, this is where it stops. Those are going to be critical points to me. So let's check it out. I'm finding half the area because I'm going to double it in the end. And it is 1/2 the integral. We'll talk bounds in a minute. But what's the outer part of this? Like if I were to look at this, I don't know that I've got it. I can use this. If I do the outer part of this, if I kind of do my remember the representative rectangles from back in the day? If I look at the outer part, well, that's the circle. The circle is 1 squared minus the inner part, which is your 1 minus cosine of theta squared. And then that's with respect to theta. Because see how there's a hole in the middle? they didn't ask me for that holy part. All right, bounds. Well, what's this? This is starting at 0, right? And what's this? This is pi over 2. Check that out. Like the regular old unit circle, you've got 0 and pi over 2. So you're going to calculate out this area and then you're going to double it. And your answer is 1.2146. So really not that hard. That one isn't really so bad. Probably easier than some others we've done. All right, couple problems. Number 2's first. Find the area of the common interior of the polar graphs 2 cosine of theta lying on the x-axis and r equals 2 sine of theta lining up on the y-axis. So first thing you want to do is graph them because who knows where these are. So I've got one circle, by the way they're both the same size. So I've got one circle that is lying on the y-axis and I've got one up here that is on the, I'm sorry I said that wrong, but I drew it right. One that's lying on the x-axis and one that's lying on the y-axis. They're both the same size, and so when I go to figure out the area where they are common interior, that's this guy in here. So my points that I'm concerned about are here and here. Let's set up the area formula. Well, the area is going to be, does it change? So if I were to draw that intersecting line like we've been talking about, what's on the right does change, and you can see that. So I need to have 2 area formulas. One that goes for this part to the left and one that goes for the part to the, well, this part that's to the right and the other part that's to the left of that intersecting line. Where does that happen? So let's figure this out. My area formula is going to be 1/2 an integral. We'll talk bounds in a minute. And I'm starting with the guy that is, if I look at this part over here, it's the circle that's lying on the y-axis. Well, that's your sine guy. So it's going to be 2 sine of theta squared d theta. And I'm going to add it with the guy that is this guy, which is now part of the cosine circle. So he is 2 cosine of theta squared d theta. And then the question comes in, well, what's the intersection points? Well, the first one, well, let's set them equal to one another because that's where they're going to intersect. If I have 2 cosine of theta equals 2 sine of theta, I can divide both by 2 and forget about it. And then I can sine of theta over cosine of theta. If I divide both sides by cosine, then that equals 1. Well, what do you know sine over cosine is? And we know that that's tangent. This is on your unit circle. Where would that be? In this first quadrant, because I don't care about any of the rest of this, where the tangent is equal to 1, where y is equal to x. And where y is equal to x is going to be a theta value of pi over 4. So this is your theta of pi over 4. All right, let's see if we can set these boundaries up. This one's 0, right? This is 0. There it is. Then I get to pi over 4. Well, this is pi over 4. It picks up on the other side of pi over 4 and closes up. When I close up, now I'm along the pi over 2 line. And so there's your setup. And so you're going to go through again, put this in your calculator. This is an area. You don't have to double it like we have with others. It's just the area of those 2 pieces. And so your area is going to be 0.5708. All right, there are 2 more, and then we're calling it a day. Number 5 is next on my list. I think we talked about these in class, like how you could figure out what the area is for one of these when you're playing that game of like how do you calculate that out. Okay, so the figure below shows graphs of the polar curve. That's the rose petals that you're looking at, 3 cosine of 3 theta. In fact, we saw that function in the last section, I think. What's the sum of the areas of the shaded region? So if I'm thinking about this, what I really need to do geometrically is figure out the area of the circle and subtract away the area of the polar of those rose petals. Well, let's think this is relatively easy. What's the area of the circle? Has a radius of 3. Pi r squared. If I'm thinking pi r squared, then I'm thinking pi times 9 or 9 pi. So ultimately that's going to be my area of the circle. And what I want to do is subtract away what the area of the polar is. So let's think polar. Well, my polar is, my polar is, let's do my area. Let me think about this. I'm going to think about what it is for one petal. So if I go for one petal, and I'm going to go for this guy here, then my polar is going to be 1/3. I'm only figuring out what 1/3 of the area is using this petal. Well, what's the area formula for polars? 1/2 the integral, we'll talk bounds in a minute, of 3 cosine of 3 theta squared d theta. Let's talk bounds. If I go bounding, I want to know where these two things intersect. Well, you know that this is a 0, but the question is, what's this out here? Like, where am I going with this thing, and how are my bounds going to go? So I'm going to take 3 cosine of 3 theta, and I want to know when it equals 3. This point here is 3. All right, divide by 3. Cosine of 3 theta equals 1. Where's the cosine 1? All right, cosine 1 is at pi over 2. Cosine of 1. Cosine equals 1 at cosine. Why am I thinking funny? I think my work that I just have on my paper is wrong. So cosine equals 1. So if I'm thinking that would be where 1 equals the coordinate 1, 0. So I would have 3 theta equals, where it's 1 would be 0, right? Where it's 1, it would be 2 pi I don't know that this is going to work. Let's see. I'm in a dilemma, kids. I wish you were here. All right, so I have 3 theta. Cosine equals 1. This would be 1, 0, but it's not. Here's what I have and why I'm in a dilemma here. I have, take this away. I might rewrite that, but hold on a second. I have the cosine of 3 theta equals 1, and that means I said 3 theta equals pi over 2. That's what I said, which is going to give me a theta that's pi over 6. I actually like this answer, but my dilemma is, if I am the cosine, I am the x value. And the x value is 1 right here at 0, not up here at pi over 2. All right, well, I'm going to come back to why that is in a minute. If I look at this first, this came up in section 9.8. Maybe let me grab those notes real fast, because I know we did these over in this guy. Here it is. All right, here's what we did back here, and this is what I was trying to get to but it isn't working out. You see how this is the same rose petal as what we have for this guy? I think I want to look at, so 3 theta equaled, it equaled 0. 3 cosine of 3 theta equaled 0. I was looking for this point. So maybe that's what I want to do, is not be looking for this guy out here, is looking for this center point instead for this problem that we're into right now. If that's the case, then that works out really well. So I'm going to lean back on this and set this equal to 0 instead of equaling it to 3, where they would intersect each other. It kind of makes sense that they would intersect at 3 because remember it's a circle with a radius of 3, and so this would be an intersecting point at 3 as well. So I'm going to go for, it's going to change up just a little bit here so that it makes our problem correct. So I know that this is 0 and I know that this is an x value of 3. So I'm going to go with where it's 0, this one here, where it starts. It starts here at 0, it comes out and goes back around. So that puts me here, which puts me at a theta of pi over 6. And then it also comes back around. We're just going to use the pi over 6. Pi over 6 will work. So pi over 6 would be, I'm thinking of it this way. This would be your theta being pi over 6. So what's the theta value going this way? And because of symmetry, this theta value would be a negative pi over 6. All right, so sorry for the delay in the middle of all that hot mess, but these are the values that you're looking for, where it starts at 0, comes around and turns back around and comes back to 0. So there are my two values that I'm putting in for my bounds. This would be negative pi over 6. This would be positive pi over 6. And so I go to my handy dandy calculator and I calculate out, my paper's all messed up here. I calculate out what that's going to be, and here's what you've got. You end up with 1/3 the area. When you calculate this particular value, it's going to be the integral that's there. You're going to have 2.356. Funny enough, that's the same answer you got back in section 9.8. This is a familiar answer. But that's what 1/3 is. So I know the area times it by 3 is 7.069. Now remember that that's not the only answer, because you want the area of the circle minus the area of the polar. So that's going to be, I'll put it so, 9 pi area of the circle, and you're going to subtract away 7.069, and ultimately that gives you 21.205. That is number 5. And then the last one that I want to do is number 10. Again, one without a picture, so you've got to draw the picture. Find the area of the common interior between r equals 4 sine of theta, r equals 2. Well, you almost can draw that without the calculator, but you can use a calculator if you want to. A 4 sine of theta lies on the y-axis with a radius of 4. And 2, r is 2, is a regular old circle with a center at the origin going like this. I probably don't have that drawn the best, but you get the idea. So the area that I'm looking at is this area in here. And so this one actually has, if I think about this, and I divide it up, there's really 3 areas that I'm looking at. Because remember, here's your intersection line. It is consistent in this one that I've got one that goes, and this is all the same kind of thing to here, right? And then I'm going to have so this is my first area. All of this is my second area, and then this is my third area. You can divide it up how you think makes sense to you. But that's the areas that I divided it up in. And that's because when I set these equal to one another to figure out these points of intersection, where are they? I'm taking 4 sine of theta, and I'm equaling it to 2. So when I divide it, I get sine of theta is 1/2. I go to my unit circle, and theta is pi over 6 and 5 pi over 6. Does that make sense for these values? And hopefully you're saying, yeah, that makes a lot of sense. This is pi over 6. This guy is 5 pi over 6. So I've got one that goes from 0 to pi over 6. That's this part here. Then I've got another one that goes from pi over 6 to 5 pi over 6. This is all consistently the other circle. But then I've got, you're back to this guy here to close it up, where it's back to your sine function. So hopefully you're seeing the difference in those two things. So here's how my areas are going to go. I'm going to go out here. Area is, first part is part number 1, 0 to pi over 6. 1/2 the integral from 0 to pi over 6, and it is the circle with the sine in it because it's the one that's along the y-axis. So this would be your 4 sine of theta squared d theta. And then you're going to add that with, now I'm in section 2, consistently all the regular circle, which is 2. So I'm going 1/2 from pi over 6 to 5 pi over 6, and that is now your sine, your regular circle. So this is 2 squared d theta. And then my third one's going to be this little section here that goes from 5 pi over 6, closing this thing up at pi, so plus 1/2 the integral from 5 pi over 6 to pi, and now I'm back to my sine function. That's what the circle is that I'm touching. So it's 4 sine of theta squared d theta. And so I go to the calculator and I add those 3 sections up, and my final best area is 4.913. And that takes care of section 9.9. So my point to that last question is sometimes you've got to divide it up into multiple types of areas to figure it out. And it's all based on consistently what circle you're touching when you get from one theta value to another theta value. And so that's kind of what number 10 was doing. Section 9.9, last one in the section. Catch me an email if you have any questions. Otherwise, I'll see you in class. Have a good one.